Use Chris Budd, who will conclude his triptych of talks.
Yeah.
The presentation on transport and mesh generation. Okay, Chris.
Thank you, Jitse. Well, it's a great pleasure to give the third of my 3 talks, and just to say again how much I've enjoyed this workshop so far, and to say thanks to all of the speakers for all of the workshop. So the last talk I gave talked a bit about the use of adaptive and moving meshes for problems with scaling invariance in 1 dimension. And Professor Brezzi, who's just turned up, said in his question, what about higher dimensions? So this is this talk. So what I'm going to do today, I'm not particularly going to look at scaling invariance, although I'll mention it briefly, is to talk about how a systematic way of generating meshes to solve PDEs in higher dimensions, both in Euclidean spaces and also on the sphere, which is a particular interest to me due to weather forecasting. And the point about the method I'm going to describe is it's essentially a geometric method, so we can build into it lots of nice structures that can be used to look at different types of PDE which also have nice structures. So this is joint work with Colin Cotter at Imperial College. He did all the clever stuff, and Andrew McRae, who is my postdoc and is now at Oxford, and he did a lot of the implementation and in fact did most of the real work that I'm going to describe. So it's called optimal transport and mesh generation in the plane and the sphere, and you'll see why I've used the term optimal transport as we go through. Okay. So the point, what I'm going to talk about is primarily mesh generation. I will talk a bit about PDEs as well, but we're going to talk about PDEs for mesh generation. So if you want to solve a PDE using a finite element method, finite volume, or whatever, you typically do this on a computational mesh. And if you have a PDE with interesting structures, such as the sort of singularities that I was describing on Wednesday, or maybe moving fronts, or you may have interesting orography if you're working in a geoscience application, then you probably don't want to use a uniform mesh. You want to use a mesh which can capture behavior on small scales. If your solution is as anisotropic, you probably want to align your mesh along anisotropic features, and you may want, as I say, to adapt the mesh to deal with complicated local geometry. So in terms of one of my favorite areas of research, which is weather forecasting, being British of course, this is relevant for the computation of things like fronts and storms. It's also very useful in data assimilation, the process of matching data to computations, which is essentially a problem in approximation theory. Meshes are useful both to calculate PDEs and to approximate functions well. So it's a good thing to compute a mesh. So here's an example of a typical sort of mesh that you might want to use. This is solving a set of equations called the ED equations. So the ED equations are a version of Navier-Stokes with various things scaled out so you don't worry about them. And they are used to look at the evolution of storms, particularly tropical storms near the equator. And here's a storm front evolving. This is height here, and this is latitude along here, longitude along here. And here is a mesh which actually started life as a uniform mesh, completely uniform rectangular mesh. Has started to evolve as a storm starts to happen and has evolved fully into the storm here. So the ED equations actually do develop singularities in finite time, which is kind of interesting. So, and you can see this sort of mesh has most of the properties you might want of a mesh. It's got a nice simple geometry, it's rectangularly connected, so every point has 4 neighbours. Away from the storm it's nice and regular, so these are not very far off from being rectangles, but within the storm itself it's highly structure. It's highly compressed, so you can get good resolution. And the other thing is that you can see that there's a slow and systematic change from here to here, so the mesh has nice differentiable properties. So these are the sort of things you might want of a typical mesh. And then on top of that, you then put a finite volume scheme, in this case, to compute the solution, or you could use discontinuous Galerkin or whatever scheme you like. Okay, so I'm going to talk about meshes in the context of something called R adaptivity. What is R adaptivity? Well, if you want to generate a mesh and your solution is evolving, so structure is developing, there are basically two ways of capturing that structure. One is to use what's called mesh refinement. So in mesh refinement, if you have a mesh like this and you decide something interesting is happening here, then you might want to refine it, and you might want to refine it, and so on. So that is mesh refinement, or adaptive meshing, simply. Alternatively, you might wish to relocate, so you might start with mesh points here, like this, and something's interesting here, so you simply move these points here towards where something's interesting, but you don't change the number of mesh points or their connectivity. So that is called R adaptivity, or relocation adaptivity, where we relocate the vertices of the mesh, preserving connectivity and topology. Why do I like this? Well, when you do this dynamically, you get a moving mesh method. The mesh and the solution evolve together. They become, as it were, a super dynamical system, and you can build then a lot of geometrical structure into the way you're doing things. You can even preserve Lie symmetries and all sorts of stuff like that, in just the same way as I showed that you could do for the one-dimensional problem I talked about on Wednesday. With these sort of things, although they're straightforward to implement and a huge amount of software has been developed along these sort of things, you don't have the same sort of nice geometric structures that you can build in. So various advantages of this above and beyond that. First, you've got this nice smooth variation in the mesh, which tends to lead to much better error estimates. Secondly, you've got control over global mesh regularity. When you do this, you refine what's going on there, but you have no idea what's going on here. It's a purely local approach, whereas this, you're kind of moving all your mesh points together, so you've actually got a lot of global control. And I'll talk a bit about how we can exploit that later in the talk. Thirdly, the mesh topology is unchanged. One of the problems, again, with adaptive meshes like this is that your data structures become horrendous as you try to work out how all the bits talk to each other, and you end up doing all sorts of really fancy stuff involving fractals, and you don't need to do that in this case. And also, this case is way, way, way easier to parallelize because all your load balancing is good. So there's a lot of reasons why this is a good thing to do. So let's give you an example of a moving mesh. This is moving mesh 101, as it were. So we're going to have a look at a mesh on the sphere. We'll come back to the sphere quite a lot. So here is a mesh which is initially a fairly uniform mesh on the sphere. It's mostly hexagons, although there's the odd pentagon every so often, which is that's part of the hairy ball theorem that you end up doing that. So I'm going to imagine we've got some sort of feature here which is going to move around on the sphere, and we are going to see if we can follow that feature with the mesh. So here we go. And as you can see, it follows it around really kind of nicely. The rest of the mesh kind of doesn't do very much, which is kind of the idea. I'll just run that once again. Okay. And you can kind of see how that works. So that's what we're going to kind of do in this talk. I'm going to show you how that works. Right, let's go back to where we were. Right, so that's the advantage of moving meshes. There are various disadvantages. One principal disadvantage is that you have to have some sort of procedure for moving your points. Typically that's a PDE, which you have to solve, so you add extra complexity. This doesn't worry me very much. If by moving the mesh I can solve a problem with, say, 100 mesh points, that without moving I'd need 1,000,000 mesh points, I don't mind doing a little bit extra work to move those 100 points around. You've got various constraints with the fact that you're always working with a finite number of points. There are certain problems you simply do need points for. You can get skew meshes with long thin triangles. Whenever I put my meshes in front of finite element people, they all kind of panic, and then I have to explain to them they shouldn't be panicking. I'll talk a bit about this in a minute. And the primary reason that moving mesh points have generally had bad publicity is there's a phenomenon called mesh tangling, where mesh points kind of move over the top of each other, and once that happens you're dead. And I shall show you, using the techniques that we are going to talk about, that this doesn't occur in the sort of methods that we're going to use. Right, so yes?
Can you think of this as having a surface, with PDE on a surface, that the mesh is a surface?
Well, that's exactly what we're going to talk about, yeah. We're going to look at the mesh on the surface of a sphere.
Not the mesh on the surface, but the mesh itself is a surface.
Yes, I suppose you could certainly think about it that way, yeah. Yeah, well, let's talk about that.
You mean if you interpolate the mesh,
Yeah.
you have an approximated surface?
Well, that may be coming when I talk about the sphere and how we do it on the sphere. That might become clear. Right, so how are we going to do this? When we looked at the moving mesh problem in one dimension, I thought of having a mesh described by a function x of psi, and then the moving mesh equation we used was sum m of x, which we call the monitor function, times the density, dx by dx psi, is equal to some constant I'll call theta. That's called the equidistribution equation in one dimension. In higher dimensions, we merely replace this by its exact equivalent, where we again have a monitor function m, which we can control and which describes some feature of the solution we think is interesting. In this time, we multiply by the cell area or cell volume, and that again has to be constant. So this is our basic equation. It's a measure equation. It's basically saying that the local measure is controlled by this monitor function.
Charlie Elliott showed a moving mesh based on harmonic maps.
Yeah.
Would that fit into this framework?
Well, every mesh fits into this framework by the Radon-Nikodym theorem. So the Radon-Nikodym theorem says whatever map you've got, there's some underlying measure, density, related to that map. And so every type of moving mesh can be put into that frame, if you choose your M correctly. So the answer is yes, but I'm not quite sure what. How do you choose them? Well, there's many ways to do it. One is you use some sort of a priori estimate of the solution error, which is typically, you might have this related to the gradient of the solution or the curvature. And that's pretty widely used. An alternative is to base it on some physics or understanding of the problem. So a meteorologist will always tell you vorticity is important in weather forecasting, so we just take it to be the vorticity. And on Wednesday, I talked in one dimension how you want to choose monitor functions which are scale invariant, and you can build that all into 2 and 3 dimensions just the same way. The third way, if you're really clever, you might have some a posteriori error estimate, and then you can use that to control the M. So there's many different ways of doing it. Okay, typically I would normally use physics. Okay, so how do you generate a mesh? Well, the best way to think about mesh generation is in terms of maps, and that avoids all sorts of complicated problems with geometry and so on. So the way we're going to generate it is we're going to have what we call a computational mesh, which sits inside the computer and we don't touch, which has some nice properties. It can be triangles, rectangles, whatever, but it's nice and regular. And the computational coordinate are called psi. And then we have some map from that into our physical space, and that map induces a mesh from that underlying computational mesh. Okay. So the whole of the mesh is described in terms of the map, and the connectivity is the same as the connectivity over here. So that's our mesh. So this is what I'd call a ring mesh being generated here by a typical map. Okay, so there we have it. We have the map. The Jacobian of that map will be something, whatever it is, I'll call it J, and then the equidistribution equation becomes m det J is some sort of constant. So that sits underneath everything we do, and as I said, by the Radon-Nikodym theorem, that's not particularly restrictive. So that is our equidistribution equation, mj is theta. And that was exactly the equation I was writing down in one dimension on Wednesday. Okay, so there's our equation. As I wrote it down on Wednesday, I didn't say very much about it. It's very easy to solve in 1D. It has a unique solution. Essentially, if I ask you to give me an interval of length, whatever, length lambda, there's only one interval of length lambda up to translation. However, if you ask me to give you a set of area lambda, then there are many, many different sets in 2 dimensions which have that area. So this is a very non-unique statement in higher dimensions. And so there are all sorts of people who have thought about ways of regularizing this or producing some sort of uniqueness. I mean, this is related to these sort of harmonic maps that Charlie was talking about. And an idea which I came up with Jeff Williams in 2006, which by some strangeness simultaneously was thought up by people in Los Alamos at about virtually the same time, is to put some sort of global regularization onto the problem of mesh generation. Now, if you open up numerical textbooks about discretizing PDEs, they will generally say uniform meshes are good. Uniform meshes are good because you get low truncation errors because you've got sort of nice cancellations and there's no skewness problems. They're nice, good meshes. So it's not unreasonable to say, well, if I want to choose any mesh which can satisfy this, let's find the one which is as close as possible to a uniform mesh. So we thought we'd try that. And that amounts, in the simplest case, to picking a mesh X which is as close to the underlying identity as possible, and the square norm is a convenient norm to do this in because then you can prove things. So this is our constraint. It's an overall geometric constraint on our mesh, and there is a theorem which I'll talk about in a minute which says that this problem here has a unique solution which minimizes this thing here.
Isn't that a bit surprising that minimizing L2 can reduce skewness? Because
Yes.
you can't even see the derivative.
I know. Isn't it wonderful? Life is good. It's completely mad that a global constraint has local properties, but it does. Okay. Okay. It all follows from this amazing result due to Jan Brenier. So last Field's medal was awarded to, I'm desperately trying to remember the name of the guy. Sorry? Figali, who proved lots of results on optimal transport. They should not have given it to Figali. They should have given it to Brenier, because Brenier did all the real work. He basically founded the subject, and Figali did brilliant work, but if it wasn't for Brenier, he wasn't. But sadly for Brenier, he was well over 40. So I don't want to say Figali shouldn't have got it. Of course he should have got it, but Brenier should have got it first. And I find it a little bit annoying that he didn't, because he really did the fundamental work. So I hope that wasn't offensive. It wasn't meant to be. Figali most certainly deserved it. So Brenier in 1991 proved this astonishing theorem that there is a unique map which minimizes that subject to this equidistribution equation. But Brenier went a lot further than that. His proof was essentially a constructive proof. And he said that the mesh, the function that you get is the gradient of a convex scalar function, which I call the mesh potential. So in other words, the function which minimizes this and satisfies this has the property that it is the gradient of a convex function. Okay, so that was Brenier's result. And the whole of the subject sits on that result. So because it's convex, that actually immediately tells me that the minimizer here cannot have a tangling property. Tangling is all associated with loss of convexity, and Brenier's theorem says that that doesn't occur. Okay, so that's it. I'm going to slightly change this to say, I'll say that you can, any map of this form can also be described as a map of the a density plus a gradient, and this is a little bit more convenient for computations. So what we're going to do then is to find our meshes using Brenier's theorem. Is we are going to look for solutions of the equidistribution equation which have this structure here, this beautiful geometric structure. Okay, so if I substitute into the equidistribution equation, the Jacobian becomes the identity plus the Hessian of phi. The equidistribution equation then becomes this, m of x times the determinant of identity plus the Hessian of phi is theta, and in Euclidean space, for example in the plane, this is the celebrated Monge-Ampere equation here. Okay, so to find your mesh, you need to solve this beautifully fully nonlinear equation here. Now there's quite a lot of literature on the Monge-Ampere equation. For mesh generation, it's a little bit more complicated than the usual literature. The usual literature solves this where that's a function of x and y. Actually, that's not right. That shouldn't be x, and y. That should be in the computational plane. I'm sorry. So that's a function of the independent variable with Dirichlet boundary conditions. For mesh generation, this becomes a function of the dependent variable, in fact to the gradient of phi, and typically you have Neumann or periodic boundary conditions. So you have to extend the theory quite a lot, but all of the theory that's been developed in general can be worked out in this context. So the bottom line is, if you solve that, then once you solve that, then by taking its gradient, you get your mesh, and there you are. So that's how you generate a mesh in Euclidean space. Okay, now I'm interested in weather forecasting, and weather forecasting typically occurs on the sphere. So we started a project, Colin Cotter, Andrew McRae and myself, and along with Hilary Weller in Reading a few years ago, funded by NERC, to see whether we could extend these ideas onto the sphere and then start doing practical weather calculations on that. So that project actually went rather well, and a lot of what I'm going to talk about relates to that project. So the difference on the sphere is, instead of doing the Euclidean distance, you minimize this thing here, where this is your geodesic distance on the sphere. This is the Wasserstein distance. So the mesh generation on the sphere, using these ideas, becomes the question of solving the equidistribution equation here, together with minimizing that overall meshes. Okay. So 2011, I think it was 2011, anyway, a few years ago, I was attending Psycade in Vidaleith, and I was talking about some of these ideas, and I said I want to do this on the sphere, but I don't know how to do it. And someone came up to me afterwards and said, you should read papers by Robert McCann. I wish I could remember who came up to me afterwards, because that was a brilliant thing to say. Because Robert McCann at the University of Toronto has basically solved this problem. Robert was, interestingly enough, I mean, he's a pure mathematician, but a lot of his work on these sort of optimal transport ideas, this is an optimal transport condition, has been done in context of economics. Anyway, the bottom line is that Robert and his co-workers, Lerper in Paris, for example, have proved a series of results, not just for the sphere, but for general manifolds, saying that this equation here has a minimizer of the Wasserstein metric here if there is a function phi such that x is the exponential of the gradient of phi acting on the underlying space. So Brenier's theorem was it's the gradient of phi, and McCann extends that to the exponential. So that's a very, very general result for a class of what he calls C-convex manifolds. He did a lot more than that. He proved all sorts of estimates about the regularity and so on. But this is the kind of the base result that again, we set the theory on.
Does the theory say anything about the skewness of the solution?
Ultimately, yes. Ultimately, yeah. You've got to work it through a bit, but I'll talk about that towards the end. Okay, so let me talk about this a bit. So what this is saying from a kind of geometric point of view is this. Here is my manifold, which will be the sphere for most of the case, but doesn't really matter. We have a function phi, which basically maps the manifold, points in the manifold to the real line. And any old function can be thought of with those sort of properties. We want it to be decently regular. At my point psi, we can construct the gradient of phi. And of course, that doesn't sort of live on the manifold. This lies in the tangent space, sitting on that point there. So there is my gradient sitting up there. And we then have to apply the exponential map. And what the exponential map does is it takes that vector in the tangent plane down onto the manifold itself to a point x sitting over there on the manifold, and that allows you to find this map. Okay, so that's the basic principle. So intuitively, what is this thing? And I know I'm in an audience where lots of people know lots of things about exponential maps, so I won't witter on too much, but broadly speaking, for our context, we go along a geodesic from here in the direction of grad phi, a distance of grad phi, and that gives you the exponential map. In 1D, in Euclidean space, or on the plane, the exponential map is exactly what we wrote down earlier. It's the identity plus the gradient of phi. And what's really nice is that if you look on the sphere, there's an explicit form for the exponential map. It's called the Rodriguez map. And there it is. That's the Rodriguez map, where capital R is the radius of the sphere. So this is something we make very, very extensive use of in our work. The Rodriguez map rather nicely goes back. Who are interested in the sphere? Well, apart from meteorologists, navigators. So people who are typically using celestial navigation, and so a lot of this sort of theory was developed in the context of celestial navigation, or indeed of geodesy on the sphere. So that's if you want to find good results, that's the way you kind of look. So that's the Rodriguez map, so in its explicit exponential map from the tangent plane onto the sphere, and there it is acting. So if I want to do my map, as I say, It's really nice. I take my phi, I calculate grad phi, I apply the Rodriguez map, and that gives me the map onto the sphere. Okay. So that's how I generate the meshes. It doesn't say how I calculate phi in the first place. I'll talk about that in a second. But once we've got the phi, that's how we produce the map on the sphere. And as you can see, I say it's got beautiful geometry all associated with it. Okay, how do we do the meshing? Well, the basic idea is this. We might have a sort of patch of stuff there, and we want to kind of map that. So we have a phi, we go through this process, that maps me onto another patch there. That's my exponential map acting. And in order to do meshing, I'm very interested to know how the area of this compares to the area of that. So we have a ratio R, which does that. So in Euclidean space, that area is just a determinant of the Jacobian, which works out as being 1 plus the determinant of 1, the identity, plus the Hessian of the function phi. And we needed to produce an equivalent thing which did the same for the sphere, and this is it. This is the equivalent scaling on the sphere, which looks like the Monge-Ampere operator on the plane, and then we're going to control that using the monitor function here. Okay, now I can claim no responsibility for this. Colin and Alan, Andrew and I and Hilary had a sort of big group discussion where we realized that we needed to produce this object, and we all went off to try and work out what it was. And then I got an email from Colin. Basically, it was near Christmas, and Colin had taken his daughter to a birthday party and had dropped his daughter off, and he had nothing to do but wait whilst they ate jelly and ice cream. So he went off to Starbucks and beavered away and came up with this formula, photographed it, and sent it to me by email. So that was the product of a children's Christmas party, essentially. So this is Colin's formula, and it works a treat. It really does. If you give me a phi, we can calculate the exponential using Rodriguez map. These are various projection operators, and this allows us to work out the ratio here of the areas, and then we can control that through the monitor function here. Okay. So that's what we need to solve to find meshes on the sphere. I've asked around and no one seems to have a good name for this equation, so we call it a Monge-Ampere-like equation, or Monge-Ampere equation on the sphere. So if anyone knows this equation and can come up with a better name, please let me know. But that's what we solve.
What is KP and PC?
These are the unit normals in these two directions. So so it's KP is that, and KC is that. Yeah.
And this tensor product is like KC times the transpose of KC?
Yes, that's right, yeah. Basically the way this is working is that we pretend that we're not working in the sphere, that we're working in 3 dimensions. We embed things in 3 dimensions, and so we take our set here, we kind of extend it up to a little cylinder, the same sort of thing. We map it over to some sort of cylinder over here. We look at the ratio of the volumes, but only look at because we keep it as a constant thing, that the volume scales, the area scales the same way as the volume. So that's how that you come up with this. Okay, so let me tell you how we solve things now. So having shown you how we do the basic construction and saying we want to solve these equations, we now actually have to go off and solve them. So if I want to generate a mesh on the plane, we need to solve m grad phi, determinant of I plus the Hessian of phi is a constant. That's our basic equation we want to solve on the plane. If you want to solve it on the sphere, it's m e to the grad phi times this ghastly thing here, det of stuff. Okay. So that's my Monge-Ampere-like equation on the sphere. So these are the things that we need to solve. Right. How do we do it? Well, we do it using a sort of mixed approach, which goes back to work by Tristan Pryor. Tristan is currently at Reading, but I'm very proud to say that he'll be joining us at Bath later on this year. So Tristan did a lot of work on the Monge-Ampere equation, and Lakis was his student. And his basic idea was that you do this as a mixed approach. You have a variable sigma, which is on the plane going to be the Laplacian, the Hessian of phi. Well, it's a tensor rather than a number of n, doesn't matter. And then you take this equation and you express it in mixed form. So here we have the basic equation here. There's our equation for sigma, and you put them both in weak form and solving using finite element. So this is a perfectly good way of solving it, which is way better than the finite difference methods that I personally used earlier before coming across Pryor's work. And you need to use different types of elements depending on whether you're looking at sigma 1 or sigma or phi. So that's
what was wrong with the finite difference methods?
it's just they get blinking awkward to use, and they're fairly messy, and you can't prove very much about them. There's nothing wrong with them. So this is then the thing that we need to do to solve this system. We have to solve this Galerkin system here. So it's nonlinear. In fact, it's fully nonlinear. Everything's nonlinear that could be nonlinear. And there are a number of different ways of solving this. Again, my original work with Williams, we introduced a sort of time-dependent thing, and we called that the parabolic Monge-Ampere equation, which broadly speaking amounted to putting a phi t on the left side of this, which was kind of okay. It worked, but rapidly showed its limitations. And so the techniques that we're using here are extensions and significant developments of that. So the first one we looked at was a relaxation method based on some work of Anu in the audience. I hope, have I spelt your name correctly there? Or? Yes, good. Thank you. So this is what is called Uanu iteration, which is a paper you published in the IMA journal, I think, numerical analysis. That dodgy journal, very dodgy editors. So Uanu iteration, as we call it, takes the Monge-Ampere equation here and thinks of this as a fixed point problem. So this is the fixed point iteration, and delta here is some sort of relaxation parameter. And then you can discretize that in a Galerkin frame. So this is the Galerkin discretization of the Uanu iteration, and also that is again the discretization of the second part of the mixed finite element thing. And basically this converges, it's good, providing this delta here is sufficiently small. So you have to sort of experiment around a bit to find something which works. But if you do that, it kind of does work. And once you've worked out what your phi is, this is kind of the process that you do. You then recover the basic x by looking at the gradient and combining the various gradients in different directions. and you need to solve various of these Poisson problems over here and so on, and you do those using typically mixed finite element preconditioned conjugate gradient type methods. Okay, so that's the procedure. Let's have a look at it working. So we're going to have a look at two quite related examples. On the left we have a monitor function which is red where it's big and blue when it isn't, and the ratio here is about 50:1. So in this, we call this a ring. We're going to try to concentrate mesh points in the ring. On the right we're going to have a bell where we're going to try and concentrate the mesh points in this bit here. So these are our two examples. And this is the sort of mesh that you get. I put this up earlier, but you can kind of see that you get with the ring. So this is using a fundamentally rectangular mesh, and as you say, it's beautifully concentrated points in here. These points actually align themselves quite well along the ring, very regular here, and you get this kind of leaf-like structure here. This is the convergence. So what we're doing here is we're iterating using the Iwanu iteration and seeing how rapidly that solves the Monge-Ampère equation. And you can see after about 200 iterations the residual has gone down by 8 orders of magnitude. So it's doing a perfectly reasonable job. That's a typical sort of mesh that you get for the bell, where you're concentrating mesh points in here. So in here the mesh is extremely regular and rectangular. Outside here we get what I call a sort of clover leaf pattern. All of this you can work out analytically, and you can work out the skewness and everything to see what's going on. And we use these sort of meshes a great deal to calculate blow-up on. So if I'm looking at a problem which has a singularity which is developing near the origin, and I'm solving that on a rectangular domain in 2D, then this is the sort of mesh that I would typically be using to calculate that. It's very, very compressed in the middle, which is why I want it nice and regular over here. I'm not really too worried about it being a bit skew around here, because the solution is really quite small there, and you don't pick up really any error from that bit. Again, if we do the iteration, it converges linearly as you would expect. Takes a bit longer, this one, because it's a somewhat more severe geometry. Okay, problem with that is that it is a bit slow. When you're calculating PDEs, the last thing you want to do is spend a lot of time calculating your mesh, because actually you're not interested in the mesh, you're interested in the solution of the PDE. So really we want something which is a bit faster if we're going to solve for PDEs, and the natural thing to use is some sort of Newton step. So there's our residual. A full Newton step is, but Newton is an extremely dangerous method whenever you use it on any problem, because if you take a Newton step, it gives you a direction to go in, and you've got really no idea whether that direction is going to have any nice geometric properties at all, and might well wreck all the geometric structure. And certainly in our case it does, and if you apply a Newton method to the ring problem, starting with a nice uniform mesh, it gives you a tangled mesh immediately. Well, not immediately, but pretty fast. And that's because the Newton method isn't respecting the underlying structure in the problem, which gives you the convexity you need to prevent tangling. So you had to work a bit, and what we found worked much better, and we could get some results on, was using a quasi-Newton method, where the Jacobian ignored certain dependencies, and we use a sort of fairly robust line search method. So you can, as the details of this are in the paper that we've, well, the two papers that we've written in this. So quasi-Newton method, more control over the step size. You don't quite get the quadratic, but it's not bad. And linear solver using GMRes and all that sort of stuff, if you're interested. And this is for the ring mesh, which we looked at earlier. The ultimate mesh looks exactly the same, so I don't need to put it up. This is the Oanu iteration here, which does a perfectly good job but goes down linearly, and the Newton method far faster. Okay. So you're getting this essentially quadratic type convergence. So that's good. And that's doing it for the bell. So you fully converge in about 100 iterations. On the sphere, we basically do very much the same. Now we've got the right structure here. There's our structure. Again, you use a mixed finite element. That ghastly thing there is the mixed finite element equivalent of the sphere, of the plane. And so we did all that and confidently plugged in, and we thought, well, the Oanu iteration worked brilliantly, nice and robust. Let's try it. We took this example, which is a famous test problem in weather forecasting. It's called the Ringler problem, where you're trying to concentrate mesh points in a particular region. So if you wanted to know what was going on over Europe, or possibly America or New Zealand or whatever, you might want to concentrate more on mesh points there and not worry about so many other places. So this is the Ringler one, where you're going to basically compute concentrate points into this region. Gamma here controls the amount of sharpness in the mesh, essentially how rapidly you're going to change. So if gamma is small, you've got a much sharper mesh, and if gamma is large, you've got a very gentle mesh. And when we tried the relaxation, we found that gamma is a half worked fine, but everything else didn't work at all. In other words, we could compute a very gentle mesh, but not very much. And it took us 6 months to work out what we were doing wrong. We should have spoken to Doug, and then we would have realized immediately, because you'll see what was going wrong. So we tried a little trick. Can I recommend this trick to everyone? It's a really good trick. If you want to do a lot of work on a problem, get as far away you can from your institution and take your postdoc with you. So we went to Canada theoretically to work with Bob Russell and various other people there. We actually ended up simply working with each other for a long time, away from all our distractions, and we were sitting outside the UBC canteen when suddenly we had our breakthrough. So it's a really good trick. Get as far away from your institution as possible and take your postdoc with you. I recommend it. It's a little bit hard to write that into a grant proposal. But anyway, what we realised, or to be accurate, what Andrew realised was to get this to work, you really have to work quite carefully about how you mesh up the underlying manifold. So I think someone said this. So the key was to use much higher order biquadratic representation of the sphere. Where we were going wrong was that we weren't representing the sphere surface properly. And once we'd done that, it all worked, and this was the convergence, as you might expect. It's much better for the more gentle meshes and slower for the more acute meshes, but it still works. And these are the sort of meshes that you get. So one of the types of mesh that is being they're converting the codes over onto in the Met Office are what are called cube sphere meshes. So cube sphere is where you take a cube, put the sphere in the middle, mesh the cube, and then project that mesh down onto the sphere. So that's the basic cube sphere, which is an improvement over latitude-longitude meshes. I don't particularly like it because it's got corners in it, but anyway. But this is the sort of mesh that a cube sphere will distort to using our methods, putting all the points where you kind of need them. That's the back end of it, so it's kind of regular one side and better the other. This is a mesh that you might generate where you want to concentrate them again in a region, but instead of using cube sphere, you use a mesh which I think much nicer, which is the icosahedral mesh. And so it's put all these things here. Really interestingly, although we start with a mesh which is basically hexagonal, it picks up also the pentagonal structure. There's a lot of interesting geometry going on in these. This is just a sort of test case to show what can be done. We imagined that there were two ring-like structures on the sphere which were talking to each other, and we asked it to mesh that, and it did a very nice job. So there's one of our rings with the mesh aligning along it, there's another one aligning along it, and over here it kind of manages to just work out what to do to fit them all together. So again, you can see there's no tangling there. Mesh regularity, which is what you were talking about, Robert. So the mesh regularity essentially follows from the regularity properties of the Monge-Ampère equation. There's a thing called the skewness factor. So if you're looking at a mesh is locally going to be generated by this Jacobian of the map. The Jacobian on a two-dimensional manifold has two eigenvalues, lambda 1 and lambda 2. The product of lambda 1 and lambda 2 gives you the size, which I'll call the scaling S. And this thing, the ratio of the eigenvalues in some symmetrized form, gives you what we call the skewness. And when you look at the error estimates associated with finite element interpolation, the error estimates use both the scale and the skewness. They kind of combine together. And ideally you want to control both of them. And the Monge-Ampère equation has so much regularity associated with it, you can get really quite nice estimates. So as I say, McCann did this sort of work, and then Lerper in Paris did a huge amount of work following on from that. And one thing which is interesting, and it shows you that research sometimes doesn't go quite the way you expect. We got this money for this big grant to work on the sphere, and the purpose of, when we said the grant, they said this is going to be very challenging and we need lots of money because it's going to be really hard, blah, 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 blah. It turns out that the sphere is easier than Euclidean space. The regularity of the Monge-Ampère equation on the sphere is better than it is on Euclidean space. And that's because spheres have positive curvature and they've got no boundary. On the plane you've got a boundary and you've got no curvature. That actually makes the solutions less regular. So it turned out we got lots of money to do a problem which was easier than one we could solve earlier.
Now you have time to do hyperbolic space as well.
Absolutely. That's on the cards. No, more to the point, I need to do manifolds with boundaries which are not connected. That's really hard, and that's really hard. So basically the bottom line is you can get controls over these two, not kind of as much as I'd like, but some, and more recently I've written a paper on that. But it's nice that we can use all this, and I'd like to thank Mike Cullen in particular, who pointed me in the direction of Lerper's work. Mike should of course also have got the Fields Medal along with Figali and Brenier, but he's well over the age of 40. Just to show you how we do this, the great advantage of working with someone like Colin Cotter is that Colin not only is really good at analysis, but is extremely good on the computational side. He and his colleague David Ham have been prime developers of something called Fardrake, which is code which allows you to kind of write finite element stuff in a sort of high-level Python type environment, and then the code just sort of all works it out. And this is the entire code that we use to generate our mesh, solving the Monge-Ampère equations. So in Fardrake you say, what sort of mesh do you want? Cube sphere. What sort of function spaces do I want? There they are. Don't need to worry about that. This is where we set up, that's the gradient of phi, the modulus of the gradient. This is the Rodriguez exponential map. There it is. There's the projection, and that's the Monge-Ampère equation. Great, it's so easy to formulate in Fardrake. It then generates tons of C code like that and goes off and solves the problem. Just to say, you can walk this all over and do quasi-Newton. You can speed things up a bit. I won't talk about this, it's not so important, only got a few minutes to go. How do we use these things? Well, there's two things you can use a mesh for. One is that once you've generated a mesh, you can interpolate functions on it, and you get better approximation properties. In meteorology, this is really, really important. If you want to combine a forecast with data, you need to be able to properly represent your data, properly represent your function. This is a thing called data assimilation. This is an example of a rainstorm hitting the UK. You can't really see the UK. Bristol and Bath are about there. This is a big three-dimensional problem. That's the mesh that we generated for that in 3D. Took about 5 minutes to generate that mesh using our methods. And I'm very proud to say that these methods are fast enough and robust enough that they are actually used all the time now in UK weather forecasts. The real work was done by Chiara Piccolo, Mike Cullen and Phil Brown, who took these ideas but turned them into Met Office code and got something which worked. So I'm very pleased about that. The other thing, of course, you want to do is you want to couple these things to PDEs. Essentially, that's a whole other story. I could give an entire lecture on that. But just to say the way it essentially works is you typically discretize your PDE on the mesh that you've got using some sort of discontinuous Galerkin approach. DG is useful because it doesn't worry so much about non-structured meshes. Solve on that, then that gives you a solution. You then calculate a new mesh using the Monge-Ampere method that I described. You interpolate that, your solution onto that new mesh, taking care to get mass conservation and stuff like that, and repeat and repeat and repeat. Now that's missing out a ton of detail, but more or less it works. And I thought I'd just give a couple of examples before I stop of the sort of solutions that you can get. So the first one is, it's not the right one. Oh, actually it'll do. This is a two-dimensional, this is solving nothing more than just the continuity equation on a periodic domain, and you can see the solution and the mesh evolving together. There we are. You see the mesh points come into the solution and come out, but stay fairly regular. Let's have a look at something on the sphere. Oh, I don't seem to have got the one on the sphere. I'll do. Oh, there it is. Sorry, apologies. Again, this is solving the advection equation with two lumps of stuff. On the left, we have the front of the sphere. On the right, we have the back of the sphere, and you'll see mesh points moving in and out of the solution. But it keeps it pretty sharp. And one of the tests for these sort of calculations is whether you get back to the original at the end of your calculation. And you do. And the last one we'll have a look at is a thing called the Gilevsky test problem, which is shallow water equations. And these generate a sort of singularity, start generating sort of structure up here. And we can sort of follow that. All these calculations were done by Andrew. Nothing might happen for a while, and then things start to happen. Here we go. Again, we've got the front and the back of the sphere. And you can see the mesh points nicely moving in as the solution evolves. Okay, well, just to conclude, my time's basically up. I've taken you through the problems, but I'll tell you about the problems over lunch. So essentially, we can produce these sort of optimally transported meshes on this plane and on the sphere by solving Monge-Ampere equations. The Iwanu relaxation is bulletproof; it works, but it takes a long time. Quasi-Newton seems to work pretty well most of the time, and that seems to be the method of choice for these sort of problems if you want something which works quickly. And it's very easy to code up using Filedrake, and coupling to PDEs works so far. And just to link it up with the talk on Wednesday, you can easily couple it to scale invariance as well, just by choosing the right monitor function. And so it works very well for these sort of blow-up problems. And if anyone's interested, here we are. And just to say what I'm working on at the moment, I'm working on the dreaded problem of the CFL number, which is how you get over time step restrictions when you use adaptive meshes, which is quite a hard problem. And at that point, I'll stop. Thank you very much.
Okay, do we have any questions for Chris?
Roberts.
Just on the last bit, coupling to PDEs.
Yes.
If I understand correctly, you're now making a DAE where the algebraic part is the Monge-Ampere equation. Is that right?
Well,
You've abandoned your parabolic.
okay, so the earlier techniques that I used, and which I still like, is that you solve the Monge-Ampere equation and the PDE simultaneously. That turns out to be very stiff for these higher order
My
problems.
question then is how
So we tend to do
it. It's difficult to get higher order in time with what you sketched on your
No,
slide?
you don't. What you do is you do a higher order in time DG to evolve your solution.
Yeah.
You then evolve Monge-Ampere by solving Quasi-Newton, so you're not worried about time. And once that generates a mesh, you project your PDE solution onto that new mesh. It's not as nice as doing them together, but the doing them together methods seems to lead to unstable instabilities for reasons that we don't understand.
And then how many iterations do you have to do on the grid each?
Not too many. We typically do about 5 or 6. As I say, the point of what we're trying to do, what you want with meshing is something which produces something reasonable fast, because it doesn't actually matter if you exactly solve. Yeah.
You're always showing these very smooth solutions.
Yes.
And whether you're going to get solutions with a lot of fine structure.
Yes.
So what would you do then? Would you like smooth the monitor function, or?
Well, yeah, you generally do have to smooth the monitor function to get stability, but they should be resolving fine structure. Yeah. At the back.
Yeah, I was wondering, have you looked at doing time-independent problems, basically trying to get equipartition of error using?
Oh yes, very much so. And exactly, you can use these sort of problems in exactly that sort of way. So, so the paper I wrote with Andrew and Colin recently, we spent quite a lot of time doing exactly that. Okay.
Okay,
Next time.
Chris again.